this is Freddie Witherden. Freddie Witherden studied physics with theoretical physics at Imperial College London between 2008 and 2012, earning an MS degree with first-class honors. In September of 2012, Freddie started a PhD in computational fluid dynamics in the Department of Aeronautics at Imperial College London under the supervision of Dr. Peter Vincent and graduated in December 2015. He's currently an assistant professor of ocean engineering at Texas A&M University. Freddie's main research interests are in the development of simple and efficient high-order methods for modern CPU, GPU platforms. The primary vehicle for this is the flux reconstruction approach proposed by Wynn and NASA Glenn in 2007. Using the FR approach, it's possible to cover both discontinuous Galerkin and spectral difference schemes, along with various new and novel methods. Furthermore, the approach is also extremely well suited to the requirements of modern many-core architectures. So Freddie's going to give a talk on high-performance asynchronous I/O for Exascale Spectral Element Methods.
Okay, thank you, Tarek, for the introduction. And today I'm going to be talking about something a little bit different. Traditionally, I've been very much on the solver side, but today I'm going to be talking about disk I/O. So getting things, primarily solutions, out to disk as quickly as possible and discussing some of the trade-offs that you have to make there. So I'll begin with a quick bit of motivation. Why do I care about writing large files to disk? Well, fundamentally, my research interests are around the simulation of unsteady turbulent flows. And you can see a few nice examples here. So you've got low pressure and high pressure turbines, rotorcraft, aerofoils at high angles of attack, and insects. All flows that have a large degree of separation, and these flows are really challenging to simulate numerically. And a consequence of this is that these very large fluid flow simulations typically require billions of degrees of freedom. So I'm showing here in the background an MTU T161 low pressure turbine cascade that we ran a few years ago, and this simulation required some 10 billion degrees of freedom to get good turbulent statistics. Now, what that means in practice is that given this case had about 90 million elements and was run with degree 4 solution polynomials, in this case they were hexahedral elements, what we end up with is 11.35 billion degrees of freedom per equation. We're solving the compressible Navier-Stokes equations. So in 3D, we have a total of 5 equations, and thus each checkpoint file comes out at around 423 gigabytes. This is big, not too unpleasant, but unfortunately, being in the world of turbulence, what really matters to us is not so much checkpoint files, but time average statistics, as this is how we do our comparisons with experimental data, and this fundamentally is what the engineers are interested in. In this particular low pressure turbine cascade case, we had to average for our partners at MTU 206 different quantities, of which I'm showing a few of these delightful things here on the side. And thus, every time we want to write out a time average statistics file, you're looking at laying down about 17 terabytes to disk. And you need to make a call about how often you want to write these things out. More is certainly better, but when you're writing out this much data, it begins to take a serious amount of time. And so you have to begin to think about trade-offs. How often do I write these things out? And that's a trade-off between how much time do I waste writing things to disk versus how much could I lose if my simulation dies 5 hours after I wrote my last time average file. So this is roughly where we are and why we very often care about putting big files to disk. Now, I'll just do a short interlude for a few minutes on the tool that we use, PyFR, to do these simulations and where this file format development work has primarily been occurring. PyFR is a code that I started developing during my PhD and is effectively a Python implementation of the flux reconstruction or FR approach. FR being a discontinuous spectral element method that typically is equated with nodal DG. I don't want to go into too much detail about the code, but I'll just note some of our features: compressible and incompressible Navier-Stokes, arbitrary order, curved, mixed unstructured grids, typically explicit time stepping. We can do implicit at a push. And in red, I've just highlighted a few of our more unique features that we have around things such as stabilization, shock capturing, and also some things on the physics side. One point I would like to make is that we do have in situ visualization capabilities. That's through the Ascent library. And this in many cases does enable us to reduce the amount of I/O that we need to do. But at the end of the day, we still need to write out checkpoint files in case the simulation dies or the hardware has a problem. And we always have to write out time average statistics files. And so there's only so much that in situ visualization can get you. In terms of the structure of the code, it's a little bit unusual because firstly, it's written in Python. And secondly, we make very extensive use of runtime code generation. So all our kernels are in a domain-specific language. And at runtime, we translate those kernels along with parameters about your particular simulation configuration into C code, CUDA code, HIP code, OpenCL code, and even, if you like, metal code that allows us to run on the full suite of GPUs that are around today. And then those kernels are what are called by the Python outer layer that is also responsible for disk I/O and anything to do with MPI. The implementation itself is state-of-the-art in a few respects. Firstly, everything to do with kernels is internally based around a task graph structure. This is to reduce overhead and increase parallelism, and we play a lot of tricks with these task graphs to enable things such as cache blocking. Additionally, beyond just doing runtime code generation, we will also do adaptive auto-tuning. So we typically have multiple implementations of a kernel, and when we go to run your particular simulation, we'll try all of them, see which combinations work best, and do all of that at runtime. And this typically makes us very robust to changes in hardware and hardware architecture, as the auto-tuning just absorbs a lot of the differences between generations. So what this, broadly speaking, allows us to do is heterogeneous computing from a homogeneous code base. Everything from a Raspberry Pi up to a large supercomputer at a national lab, so long as it's not Aurora. Now, in terms of performance, I'll just show an example with degree 7 solution polynomials, explicit Navier-Stokes. This is very much where we are trending in terms of the types of simulations we run. Complex geometries need tetrahedra, and we typically like higher orders as they tend to be a bit more efficient. I'm going to use 12 times 105 cubed elements, and we're going to have a go on Frontier at ORNL and Alps at CSCS. Our metric for performance is the same one that you guys use, so I shouldn't have to explain it too much to this audience. It's gigadofs per second. So the translation is you have 10 to the 9 degrees of freedom in your simulation. You need 100,000 RK4 time steps. RK4 is 4 stages per step. Then, as long as you know how many gigadofs per second of compute you have, you can very easily estimate your runtime. So it's quite a nice normalized metric that factors out a lot of different things and doesn't allow you to hide poor serial performance. Okay, so on Frontier, if we use 16 ranks, which is 8 GPUs, because again, MI250X has this weird structure, 16 ranks works out to 8 actual GPUs, and on that, we get about 26 gigadofs per second.
Yes. Is this 26 on the 16 ranks or per rank?
In aggregate across all 16 ranks. So you're looking about just over 1 gigadoff per second per, I guess, GCD, 2 GCDs per GPU. So you might want to call that 8 GPU, 16 ranks. So that's in aggregate. That's the point at almost the origin of the graph. And then I'm just going to strong scale this. I don't particularly care about weak scaling. Everyone gets perfect weak scaling unless you're doing something badly wrong with these kinds of schemes. So this is where we are in terms of strong scaling. In the dashed line, I'm showing the 80% line, which I know you guys are advocates of, and it's where we like to typically work as well. And you can see we get pretty good strong scaling. It's almost perfect, going from 16 to 512 ranks, and even at 1,024 ranks, not too bad. Now, just pay attention to that baseline number of 26 gigadoffs per second, as we're now going to switch over to ALPS, which is an NVIDIA system. With that, 16 ranks on ALPS, which again, you can argue is twice as many GPUs because the 8 GH200s don't have that weird split. So adapt for that as you will. Where our baseline is now at 96 gigadoffs per second. So quite a bit more. It's a more capable GPU and a slightly nicer architecture. But what I really want you to focus on are those scaling numbers and just how crisp that scaling is. Even up to going from 16 ranks to 1,024 ranks, we are getting exceptionally good strong scaling. We've largely attributed this to the fact that this is a Grace Hopper super chip. It has fantastic bandwidth and a really good interconnect, and CUDA-aware MPI really does deliver the goods here. These are very nice scaling numbers that allow us to really push through simulations quickly, given the resources. Where we fall down a little bit is on disk I/O. Our file format in the version of PyFR you can get today, which I'm calling our legacy format, is based around parallel HDF5, which is pretty standard. We have a separate file for the mesh and the solution. That's a good thing. But the internal structure of these mesh and solution files is dependent on your domain decomposition. So if you want to run on a different number of ranks, you have to run a command that will completely rewrite your mesh and solution file as part of the repartitioning process. And this can be really expensive and a real pain. It can take several hours to do this. And you need to do that if you want to restart on a different number of ranks. So this was a big factor that was limiting some of the things that we want to do going forwards, and why I started to look into putting together a new and better file format. So with that, let's talk about requirements for a new file format. What does it need to do to be workable for us? And with this, I came up with 5 key requirements that any new format had to satisfy. Firstly, very basic one, not particularly controversial. It needs to be based around a well-established, self-documenting archival-grade container. So something like HDF5 to ensure that these files can be read 10, 15, 20, 30 years from now. Secondly, it needs to be compact. And by compact, I mean it should exhibit minimal redundancy. So we shouldn't be writing things more than once or duplicating things, as that wastes bandwidth, it wastes storage. The only exception when some duplication or redundancy may be beneficial is if it meaningfully improves usability or reduces processing time. So again, there are some trade-offs, but overall, we don't want any redundancy at all if we can avoid it. Okay, next. This was a bit more of a difficult requirement. It should be compatible with what I'm going to call the quirks of a parallel file system. I'll talk about what these are specifically later, but they are not pleasant. However, this is needed if we want to get scalability on leadership class machines. You need to be able to work with a parallel file system as badly designed as you may believe that they are, and I believe they are horrifically badly designed. Finally, they should be able to deliver good application performance, even in suboptimal environments. Suboptimal could mean you've got a silly user that's compiled things wrong. It could be you've got a system with under-provisioned disk I/O, or Nowadays, in this brave new world, you've got someone who's doing machine learning job who's decided to extract an archive with 1 billion training images into a single directory. It happens. Storage is a shared resource. And so even if you have the most beautiful setup, everything can go badly when someone else is on that system doing something they shouldn't be doing. It happens more often than it should, and I want to be robust against this. And finally, and this may be a little bit more on the controversial side, the format should be simple enough to enable ad hoc post-processing without the need for new and novel middleware. And my basis for this is just looking at how people who actually run simulations, how they post-process them. Every simulation appears to have its own unique requirements for how they want to post-process the data, and everyone has their favorite pet language that they want to do some of that post-processing in. And I want to be able to facilitate that at both the small scale and the large scale. So whatever format we come up with can't be too complicated. It needs to be pleasant to work with at the small to intermediate scales, which is realistically where most simulations actually occur. So they are my overall requirements. Now let's look into the approach. How did we go about addressing these 5 requirements with a new file format? Okay, the best way of addressing requirements 1 and 5, which is archival grade and simplicity, is with HDF5. What we put out at the end of the day should be an HDF5 file. Yes, I'm well aware there are trendier formats such as BP5, but they're not as widely deployed at the moment, and they lack the track record of HDF5. HDF5 has a proven track record and is easy to interface with from almost any programming environment you care to mention. There are great wrappers for it. People know and trust HDF5 as a file format, even if some of the libraries that support it are not the best thing in the world. So we're going to be HDF5 based. Next, if you want to be compact, that strongly suggests decoupling the geometry and the solution. I have a simulation here. What this says is you should have a mesh file that contains as much of your static geometry as possible, and then a separate file that contains the solution. Again, if you're doing AMR or you're deforming things, it becomes a bit more complicated, but to the maximum extent possible, you should be trying to decouple your static geometry from your dynamic solution, having 2 different files. Now, meshes are fundamentally a write once, read many kind of arrangement, in the sense that you create a mesh and then you may run dozens or even hundreds of simulations on that mesh as you get your simulation up and running, and then you restart it periodically every 24 hours based off of your job allocations. So what we should have here is, because they are write once, read many, they're actually quite easy to design. The only real thing you need to think about is how do you represent the elements in the mesh, and how do you represent or otherwise reconstruct the connectivity between elements. That fundamentally is what a mesh is. So what we have are elements, and those elements are defined by nodes. I'm showing some examples here at different polynomial orders. You need to somehow specify those nodes and also associate those nodes with elements. So using quadratically curved triangles is kind of a motivating example. A trivial way of specifying those quadratically curved triangles is just to represent each triangle, which is again something in 2 dimensions, as a 6 by 2 array. 6 nodal points, 2 spatial dimensions, and then you just have a bunch of those things, and they are your triangles. This is what the existing PyFR file format does. It's very easy, but it's also wasteful, because nodes are shared between multiple elements, and so you've got some redundancy. Hence, a more efficient approach is to have elements being defined in terms of node numbers, where these numbers, which I'm showing here as locks, are indices into a global nodes array, where the value m here is the number of distinct nodes in your mesh. Thus, each element is just a collection of integers saying, these are my node numbers, with the ordering being conforming to some standard that you predefine. This is arguably a better format because while it does have an extra layer of indirection, it's more compact. And what you effectively end up with here is one array per element type indexing into a global nodes array. So if you've got two different types of elements in your simulation, you'll have two arrays, and then you'll also have a nodes table. The number of nodes you need per element is fixed by the highest degree of curvature of that element. So if you have quadratically curved triangles, then you need 6 nodes to describe each of your elements. Now, you can say this is a little bit wasteful because, well, what if most of my triangles are actually linear? They're not quadratically curved. Yeah, you can play some more games and you can avoid that inefficiency, but it comes with an extra layer of complexity. And given the mesh is only ever read once, we didn't deem this a necessary optimization. If you have a quadratic triangle, just make all of your triangles quadratic as far as the mesh is concerned. Now, next thing, connectivity information. In principle, you can derive this from node numbers. You look at faces that share node numbers, and from that you can derive the connectivity array. But that's pretty inefficient, and so it's better to embed this information. And the way we decided to do it was through this additional connectivity member. So remember, we're talking about triangles here. So a triangle has 3 faces, and for each of those faces, we're going to specify who it's connected to. The way we do this is by a pair of numbers. A CIDX that says what you are connected to, and then an offset, which is sometimes optional, that says where in that thing do I need to go. This is a bit clearer with an example. So that CIDX is an index into an array that says, what am I connected to? So in this example here, CIDX 0 says you are connected to an element, which is a triangle, and it's face 0 of a triangle. CIDX 1 is an element, it's a triangle, and you are connected to face 1 of a triangle. This also lets us say if you are connected to some kind of boundary or boundary condition. So CIDX 3 would say, oh, you're on the outflow boundary. For all non-boundary connections, that off member is the index into the element array. So the CIDX allows you to say what I'm connected to, face something of a particular element type. What's the element number I'm connected to? That comes from that off member. Again, very nice, very compact, and handles boundaries and just regular internal connectivity quite uniformly. For domain decompositions, we are going to represent domain decompositions as just a big list of element numbers. So if we have a simulation that has quads and triangles, and we have 3 partitionings, then inside our mesh, what we're going to do is just write out an array where the first part of that array is, okay, what quads does rank 0 have? Then what triangles does rank 0 have? Then what quads does rank 1 have? Then what triangles does rank 1 have? And so on and so forth. Yes?
So the numbering here, there's a global number of all triangles, quads.
Yes.
When you're looking at neighbors, this is global number.
Exactly. So these numbers here are all global numbers. And the way you know where you need to read is there's a bit of metadata attached to that array that says rank 1, you need to read this region, rank 2, you need to read that region. And so everybody at that point knows their global numbers. Oh, I have these quads, I have these triangles.
How do you know where a global number on which rank a global number that you don't know but your neighbor is?
We'll get to how you figure out the neighbor connectivity. That's the fun bit, yes. So this way, partitionings are very compact, and you can embed multiple different pre-computed partitionings into a mesh. It's just an array, and the metadata tells you where you need to do your reading. Now, how can you efficiently read your elements? Well, the answer is everyone reads a contiguous chunk of every single array in the mesh file, and then you use our good friend all-to-all-v to do the redistribution. Now, all-to-all-v has a bad reputation, but that historically has more been an implementation thing rather than anything intrinsically wrong with all-to-all-v. And again, I'm only doing this at startup, and all-to-all-v is a lot faster than disk.io, so don't worry about it. A similar thing can be done for reading the nodes. After you know what elements you have, you know what nodes you have. Everyone reads their fraction of a nodes array, and then an all-to-all-v is used to redistribute that data out. So all of our actual I/O on disk is contiguous, and all-to-all-v is what's doing the dirty work of redistributing it. Now, onto the fun bit. When you're running in parallel, you need to reconstruct these connectivity arrays. It's good fun. For each face on a partition boundary, we need to determine which rank has its neighbor so we can do our MPI communication. Now, the easiest way to do this is for each rank to attempt to construct its connectivity array and then just maintain a list of unpaired faces. So where we are connected to an element that isn't a boundary and that we don't have. Now, the naive solution then is everyone has a big list of things that aren't paired. You can do a gargantuan all gather V. So everyone sends their list of everything they're looking for to everyone else. You then see what of the missing things do I have, and then you respond back with an all-to-all-V saying, yes, I have your element. This works on paper, but it doesn't scale. And if you want to see why it doesn't scale, try running the fun case of one element per rank. You will find that all gather V is gargantuan, as pretty much every bit of connectivity will be unpaired, and you will be sending hundreds of gigabytes to each rank, which it needs to trawl through. Again, not scalable, doesn't work. How do we fix this? What we do is we augment our partitioning array with its neighbor connectivity graph. So you see this particular mesh here. This has an associated connectivity graph. We say which ranks are connected to which other ranks. This is a really compact graph because in the case of a well-partitioned mesh, each rank only has a relatively small number of neighbors. So we'll associate with metadata who your neighbors are for each rank, and we'll attach that as metadata to the partitioning. Then, once we have that connectivity graph, we can pass this directly to the rather neat function neighbor all gather V. This is the neighborhood collectives that were part of the MPI3 standard. And effectively, we only send our list of unpaired faces to ranks that could actually be our neighbor. And for a well-partitioned mesh, the number of neighbors that each rank has is in general of order 1. This approach scales beautifully, just using neighborhood collectives to distribute the data to people that may actually have a chance of responding. So, with neighborhood collectives, we can very efficiently do the interface pairing at runtime with relatively little overhead. Okay. Now, on to the fun bit, solutions. Solutions are probably best described as write once, read sometimes. This is especially true in the case of checkpoint, where you may write out a checkpoint file but never use it. So what matters is how quickly can I get these things out to disk? And to understand how to do this, we need to talk about parallel file systems. The leading one in this business being Lustre. It's one of the more infamous systems out there and is loved by users and sysadmins. It never breaks, it never loses your data, and it will never take your cluster down for days at a time when it decides to get up on the wrong side of the bed. Now, the best way of thinking about Lustre in terms of a mental model is RAID 0. So instead of disks, which you'd have in RAID 0, you have object storage targets, or OSTs, and what you can do is change the number of OSTs and the stripe size on a per file basis. So, to give you an example, I have an arrangement with 6 OSTs, 6 disks. I have a 32 megabyte file, and what I'm going to do is have a 4 megabyte stripe size, and I'm going to have 3 stripes. And so, on disk, my file looks something like that, where the file itself is split in 4 megabyte chunks across 3 different disks. I can choose the stripe size, and I can choose how many stripes I want to use. The idea behind this is I/O bandwidth can scale. You add more OSTs, you can get more disk parallelism. But of course, to exploit this, you need to have multiple nodes writing to that file, because otherwise one node will quickly find itself saturated. Okay, now, Lustre has several quirks, and quirks is me being polite. And what this means is obtaining high throughput can be frustratingly difficult. Firstly, default stripe counts are often inadequate. So this is more a configuration issue, but it's not uncommon to log into a cluster and see when you create a file that it's just going to use a single stripe. So all that data goes out to one disk. Hence, unless the user knows how to use the LFS command to change that default, or unless the sysadmin has used something like progressive file layouts, performance will be poor no matter what you do. This is actually a big real-world issue. A lot of our users are stung by this. Secondly, Lustre has a somewhat baroque locking protocol. This locking behavior is infamous. Effectively, to write to a file, you have to take a lock. Obtaining locks is expensive because you have to go and ask a server, please give me a lock. And so the way Lustre works is it tries to be optimistic with its locking and will try and lock as much of the file as possible because, hey, you may want to write or read more of it, so I'll just lock whatever I can. Now, imagine a bunch of different ranks all trying to write to the same file, all trying to play this game. What you get is thrashing. So even if you have multiple ranks all writing to an independent part of a file, no overlapping whatsoever, the performance could be worse than a single file. To put this into coding sense, imagine if you were writing a multi-threaded program, instead of having individual locks to write out to memory, anytime you wanted to write out to any bit of memory in your system, your thread had to lock the entire address space. That's your brain on Lustre. Okay, so one way of avoiding these locking issues is to have each node write out its own file. This actually works really well. It bypasses the locking issue because you're the only one writing to that file. And also, since files are normally assigned an OST at random, that misconfiguration issue also disappears because You'll have lots of files, and so you'll be writing out to lots of OSTs overall. And here's some kind of data that backs it up. So this is some data I took from Moore et al., where they use 192 ranks to write out files. Their system has 24 OSTs. They're doing low-level POSIX I/O, so we can't blame it on MPI. And what they compare here is the bandwidth you can get from a file per process against a single shared file. And that single shared file is configured to use all 24 OSTs, and the stripe size of that single shared file is this transfer size here in megabytes per second. And what you can see is even when you do everything right in terms of using all of the available disks and you use nice big stripe sizes, single shared file performance is pretty tragic. And again, everyone is writing out independently. There is no overlap here in this writing, but you can see that performance is pretty atrocious. And this leads to a lot of what you'll see in the literature about the idea that single shared files don't scale. What you're seeing here is an example of that, and it's all due to this locking behavior that I talked about earlier. This is for a correctly configured system. So, file per node. Why don't we do that? Well, firstly, it goes against the requirement of simplicity. My users don't like to have solutions split across 5,000 different files, as it makes post-processing an absolute nuisance. And secondly, it also doesn't scale, because why would it? This is Lustre. And that takes us to the third problem that Lustre has in practice. Its metadata performance is bad. Practically, it can be an order of magnitude worse than NFS, which is a competing network file system. It's not a parallel file system, but it's still a network file system. And what this really atrocious metadata performance means is that you're practically limited to about 1,000 files per directory before performance starts to tail off. In contrast, you'd use something like Amazon S3, you can have 1 billion files in a bucket and it will not even blink. And that's going over the public internet. But Lustre, more than about 1,000 files per directory, you're going to have problems. So, what we could try and do then is a hybrid solution, where a bunch of ranks agree to share a file. And if you're familiar with the work of the Adios people, this is one of the things that they advocate and have had some success with. Bunch of ranks share a file, you kind of get the best of both worlds. However, it still isn't simple, as you still end up with a bunch of files and you still end up with a tunable. How many files? And so, the question then becomes, can we resolve issues 1 and 2 so that a single shared file, which is what my users want, is viable? Can we pull this off? And the answer is yes, so long as we're willing to deal with this Gordian knot, that is HDF5 and MPI I/O. The source of all of these problems around locking is because our I/O libraries are imperative rather than declarative. Lustre doesn't know what you're going to do until you do it. Whereas with, say, a declarative approach, we could say, yes, I'm this rank, I'm going to write this range of bytes. If we could do that, there would be no locking issue, because the file system could take out the right locks, there'd be no problems. That is not where HDF5 and MPIO are at the moment. They are very much imperative libraries. Their model doesn't know what it's going to do until you actually start calling functions to write stuff out to disk. And so what we're going to do is cut them out entirely. No HDF5, no MPI I/O. We're going to go straight down to the low-level POSIX layer. This opens up a few things. Firstly, by taking ownership of the I/O stack, I can trivially deal with the stripe count and the size issues. because I know how big my checkpoint file is going to be, I can make sure that it's using a good number of stripes. And we can even do this using raw IOCTLs so that we don't even depend on Lustre as a library. So what you can do is on the root rank, these are low-level POSIX calls. You do this LOV delay create flag, which says, hold off on creating my file. Then you make this IOCTL with this set stripe command that basically says, yeah, give me as many stripes as you can and make them 128 megabytes. Low level, you do this on the root rank, your file will be created using as many OSTs as are available with nice chunky 128 megabyte stripes because again, I'm writing out big files. We in fact don't do quite this. We create all the structures by hand, so you don't even need those header files. Again, this is low level, the kernel interface for Lustre. It works very nicely. Okay, what next? Well, we've created our file. Now we're going to reopen it with serial HDF5, and we're going to stub out the solution arrays. So in other words, we're going to lay down the structure of the file, and in that file, we're going to create all of our arrays. These are big, chunky arrays, and those arrays are in global order for the elements. So they are domain decomposition independent. We're going to stub out these arrays, but we're not actually going to fill them with data. We're just going to create the arrays and then take advantage of the fact that HDF5 arrays, as long as you aren't doing any funny business, are contiguous on disk. So what we're going to then do is ask HDF5, where are each of my arrays on disk? What is the byte offset of each of my arrays? Here I've got a triangle data and quad data. I'm going to find out where those two arrays start on disk. Then we can broadcast these to all of the other ranks who can then actually start doing the writing. But how do we deal with this locking issue? Well, Lustre does have a solution for this. It's called a group lock. It's been around for about 20 years. What you say is, I'm going to give up POSIX semantics. We say we know what we're doing. We don't need any consistency because, again, we're write only and our writes are non-overlapping. So Lustre lets you take out something called a group lock, which is when a bunch of ranks say, yeah, we're in cahoots with each other. We know what we're doing. Don't bother with any of this locking rubbish. Leave us alone. And Lustre, with that, will oblige, and there'll be no locking problems. We can do this because I know exactly what I'm going to be writing. MPIIO and HDF5, practically speaking, can't do this because they don't know what you're going to do next. And this group lock has some issues with being able to read your writes. Again, not a problem for us. I'm just writing out a checkpoint file. So it's all good for me, but it's something that HDF5 and MPIIO can't really take advantage of. So how do you do it? Well, you open up the file for reading and writing, and then you use another low-level I/O control to say take out a group lock, and then you just make up a group ID. Can be any number you like. Every rank does this. You then have your group lock, and you can start writing out your arrays to disk. So here I'm showing it using pwrite, where I'm going to write out my portion of the quad data at whatever the offset is of the quad array on disk. Then I'm going to go and write out my portion of the triangle data at whatever part of the triangle data I have. So each rank will then do a couple of independent write calls to write out its portion of the global array. And again, this is after doing an all-to-all to get all the data in a suitable order. So with this, a single file can scale by the virtue of taking out group blocks and then doing independent writes. But again, the writing here is not being done by MPIIO. It is not being done by HDF5. It's being done by our good friend, the pwrite syscall. Further, I can play some more tricks. In particular, I can have all of that writing done in a thread. I can spawn a thread and have those two write calls done by my thread. The result, guaranteed asynchronous I/O, no questions, no caveats. And I've got to compare here against Open MPI, as yes, in theory, MPI I/O does have non-blocking rights. But for non-blocking rights to actually be non-blocking, they depend on something called generalized requests. And depending on what mailing list post you look at, MPI/O does not currently properly support generalized requests. And so MPI/O with Romeo, which is the leading MPI/O implementation, probably is not actually asynchronous. When I launch a thread, I guarantee it's asynchronous. No funny business. And hence, I can pull my I/O out of the critical path. The only bit that's in the critical path is the root rank stubbing out the file, and then everyone taking that group lock on that file. The benefits here is we get an extreme amount of robustness, especially on abused or under-provisioned file systems. Because again, my I/O is now asynchronous. Yes, we do support having a timeout because again, you may not want it to take 15 minutes for your checkpoint files to be written out, so there is a timeout, at which point we just wait. But in general, this gives us an extremely good level of robustness to abused file systems. Because again, it's all being done in a thread, no questions asked. Finally, this approach has packaging benefits. We're in Python. We interface with HDF5 through a library called H5Py. And 95% of my users acquire H5Py by doing pip install H5Py. That, however, gets them their own version of the HDF5 library. That version is almost always serial. Previously, that would be a big deal because I would lose out on my parallel I/O for most of my users unless they know to compile H5Py from scratch against the vendor-provided parallel HDF5 library. No more, because I'm owning the I/O. I'm completely fine with a serial version of HDF5 because it's only being used to actually stub out the files on disk. In terms of how this works in practice, compared with our existing parallel HDF5 format, where you make a reasonable effort to configure both properly, you're looking at about a 5% reduction in wall clock time for I/O light simulations on well-configured systems, but closer to 15% for I/O heavy simulations in suboptimal environments. And in my experience, a lot of my users fall into that case. They write checkpoint files more often than they should. They write time average files more often than they should, and they don't bother to configure anything. Here, you're looking at closer to a 15% reduction in wall clock time, mostly because of the asynchronous nature of our writing. So, in conclusion, I've described a high-performance file format suitable for exascale discontinuous spectral element simulations, and I've outlined a suite of techniques for avoiding common pitfalls. In other words, I can get scalable single-file operation with guaranteed asynchronous I/O that is robust against users doing silly things. And the code is available in the development branch of PyFR and will debut with the next major release of PyFR.
So Freddie, you didn't say it, but the solution data is just an array of degrees of freedom per element.
Exactly. It's stored in the global ordering, because that means that when you have your solution, if you want element X, you know exactly where element X is, and that makes the solution files domain decomposition independent.
So this is cool. It's very low level and performant. It's interesting. Would be cool. It might be interesting for us too, but we do need continuous solutions.
That's no problem. What I mean by that is all of these techniques, it would apply very directly, because before you actually go writing out the solution, there is an all-to-all required, because again, everyone needs to write contiguous data. That needs to be in global order, which is not the order your ranks have it in. So there's this intermediate all-to-all before the writes happen. And so at that point, you can do any, what you might call coalescing for your, if you're with CG. So you could absolutely do a CG type approach. You may not have separate quad data, triangle data. You could just have a global set of nodes, and then the all-to-all would say, well, the first rank will write out the first million nodes, the second rank will write out next million nodes, and you just need a way of figuring out how many nodes do I have in total, and then with that total number of nodes, you just need to do the all-to-all exchange just before the writes are done. So this would generalize, and then when you're reading your solution data, you do something very similar to what we do with the mesh. So with the mesh, I showed how we have a CG-like table of nodes and elements defined by node numbers. You would just do the same thing, but for your solutions. So all of these techniques would map over very nicely. You just have an extra layer of indirection, an extra all-to-all, no worries. But the key things around, avoiding locks, getting everything in a global format, the asynchronous I/O, stubbing out these files efficiently with HDF5, that all translates over, I would say, very nicely. And you get a single pristine solution file that looks like it came from one rank at the end.
If we want to give this a try, how well is it separated from the rest of the PyFR? Is it like its own library, or is it we need to look at particular locations?
It honestly is a couple of hundred lines of code. It's really short. So again, this is kind of the right layer here. I did it in C. We actually do it in Python. It's really simple. You just need to make sure that you can do that IOCTL. That's the only bit of magic. Then the writes, you can kind of do them how you like. And I'll show, the backup. So this is roughly, how you stub out your file. You just open it with HDF5. You use create dataset. Then you set the last element, because that forces it to be written to disk. And then there's an HDF5 I/O call to get the offset of each array. So it's really simple. Then in PyFR, we wanted to avoid a dependency on Lustre. So we do all the syscall stuff ourselves. We pack all those structures that I showed earlier ourselves. If you want a dependency on the Lustre library, there are ways that you can do this, but it's really easy to do. The key realization is HDF5, if you don't do anything crazy, you get contiguous arrays. And so that's the really big decoupling factor, is once you realize that those arrays are contiguous on disk, and it's easy for your in-memory representation to match the on-disk representation, everyone is, IEEE floating point, little endian, no padding. This is actually really easy to do. And I actually, to make it more portable, I showed how to do all the relevant things in C rather than through our crazy Python abstractions, just to point out that it really isn't too hard. Once you've kind of settled on your format, the actual writing is really simple, launching the thread is really simple, and it's just broadcasting the offsets in the HDF5 file to each of the ranks. They then know their local offset, and they do some writing. It's, I hate to say it, but the writing is actually simpler than if you use the C library for HDF5, if that makes some sense, with all of its HFP something. Not syscalls are easier. You just say write here, please. Like it's simpler than using HDF5 on its own.
I have a question from Johan. What about non-conforming meshes?
Again, you'd need to come up with some description of how you represent the solution, but presumably it's just a bunch of nodes and you have solutions at those nodes. And so all of the writing stuff generalizes. The mesh was very much designed with, continuous, conforming elements, but you could certainly extend it to non-conforming. And I have some ideas about how to handle moving and deforming meshes, as in how in the solution you can embed deformation tables that say how the node should be perturbed when you read that solution to enable efficiently handling rigid and non-rigid deformations. That's not mainlined, it's just I know how it would work. And the format also supports mixed polynomial orders, element subsetting. That's all incorporated at the moment. I just didn't put it in the slides, but we can do mixed polynomial orders. We can do subsetting where you only write out a fraction of the elements, and that all fits very nicely.
Any more chat? Any more questions in the WebEx or anyone here?
So kind of related, one thing, we do some of these things very similarly. But one thing that makes sense in the moving mesh case is to keep the topology of the mesh and the connectivity in terms of indices as one file, and the coordinates of the nodes as another file that could change, could be updated.
Yeah, so...
In fact, for us, the nodes are just another finite element field. And the topology is described in terms of vertices, not all the nodes. But that's a detail.
Yep. Yes.
When you go from one partitioning to another, is there any performance consideration in the fact that your like element offsets are going to be partitioned differently, so that you're going to be jumping around in that file?
That's all handled by the all-to-alls mask, all of that. So there's kind of a global all-to-all which does all the repermuting, all the rearrangement of the data. And the same on the right side. So we're completely insulated from all of that. All of your I/O is always contiguous, and all-to-all V is more than quick enough. And again, you can play more tricks if you wanted to. You can use persistent requests if you wanted to get a little bit more out of it.
With this all-to-all, I mean, do you use some sort of rendezvous type of algorithm to figure out, or is it really all-to-all?
In the way I call it is as one big all-to-all V. In practice, the communication actually ends up being quite sparse.
Are you familiar with this rendezvous type of approaches? So Hyper uses that in the where they only know local numbers and they need to figure out who the neighbors are. In the assume partitioning, there's a paper from the Hyper team. I mean, there's 1D, so I don't know if it's applicable, but that could make things more scalable. Than full all-to-all.
The all-to-all, when I did look at doing other approaches, because you do know who you need to talk to. So you can just do I send receives pretty easily, because you know who the data is coming from and who you need to send to. So you can map it out yourself. But the MPI libraries are finally starting to improve all-to-all V. So the hand collective stuff in OpenMPI is really starting to improve all-to-all V performance. So we just leave it there, but you can, if you see that's a bottleneck, that can be optimized.
Might be worth taking a look. I think they're called rendezvous algorithms. You can agree where to meet.
Yeah.
It's supposedly more scalable.
But again, we're always going to be bottlenecked by the disks, and so we're actually in a very nice environment overall.
You kind of mentioned Aurora in passing, and I didn't see SYCL in the list of
Yeah.
Do you want to elaborate on that?
Yeah. So our approach for Intel GPUs is to hit, when we do have to run on them, is OpenCL. We do that rather than SYCL because we're, firstly, in Python, I like C APIs. CUDA and HIP both have C APIs.
Yep.
I like C APIs. Secondly, and this is the big one, because you could wrap some SYCL if you really had to, it's not the end of the world. I do runtime code generation. And I would contend that everyone who's serious in this game does some kind of runtime code generation. And the SYCL model just doesn't fit with that. It's a bit like when we're on COpenMP, you have to call out to a compiler. And then when you look at what the SYCL compiler actually does, and you look at how Intel works, their effort goes into the OpenCL. OpenCL typically gets the new features first before SYCL. If you look at, when you get the weird vendor extensions, they typically come to OpenCL before they come to some kind of SYCL extension. So we're very much in the OpenCL case. For dense operators, we get that from an Intel library called TinyTC, which is the Tiny Tensor Compiler. And that's a pretty elaborate infrastructure that can be used for DCEN. It can do, not just the generation of the operators that we need, but it can also handle fusion. So in the kind of the CG approach, where there are lots of opportunities for that, it can generate fused kernels very efficiently. And internally, it's generating OpenCL code. And that library is from Intel. It has SYCL interfaces, but internally, they're low-level library for basically doing what libxSMM does on CPUs and doing all of the fusion and that kind of thing, designed specifically for DG. It's generating OpenCL code. So until SYCL gets runtime code generation, it's a dead end, at least for our purposes, and we don't lose anything on OpenCL. I think that's also where a lot of other people have kind of iterated too. I need to do runtime code generation.
Very fair point.
And yeah, CUDA and HIP, they both have runtime compilers. SYCL just doesn't have even just the mental concept of runtime code generation outside of just invoking a separate process and writing a C++ file, which is a big issue for us. And I think, yeah, I don't know, some other people recognize that, but at least everyone that I've spoken to that's heavy into, getting the roofline performance, you're doing runtime code generation. And I can't do that with SYCL.